Okay, so we want to develop a model of the rotational modes of the ideal gas. So our basic starting point for this is going to be the quantum rotator, which we introduced in the lecture on quantum mechanics. So this is a simple model of the energy levels of a rigid rotating body. So this is our simple model of the diatomic molecule. Okay. And we saw that the energy levels of the rotator are labeled by an integer L, so they are epsilon L, where L takes values between 0 and infinity. And specifically, the energy level epsilon L is given by h bar squared over 2I times L plus 1. So here I is a parameter which tells you how much kinetic energy is associated with the rotation. It's called the moment of inertia. Okay. Now, an important point about the rotator energy levels is that they are degenerate. This means that for each value of L you have more than one possible level. And in particular, the degeneracy is such that the energy level L has 2L plus 1 levels associated with it. So epsilon L has a 2L plus 1 fold degeneracy. Okay, so we can visualize this on a graph just quickly. If I plot a graph of the energy in terms of this unit here, then if L equals 0, I get energy 0. If L equals 1, then this term gives me 2. And if L equals 2, then this is 2 times 3, which is 6. So that's up there. Okay. So these points correspond to here L is 0, L is 1, and up here L is 2. Okay. So the ground state is non-degenerate, there's just one level there. The state where L equals 1 has a 2L plus 1, that's a 3-fold degeneracy, so there are 3 levels there. When L equals 2, that gives you 5, so you have a 5-fold level degeneracy there. Okay. So two things you can note from this picture is that as I go to higher values of L and higher values of energy, the gap between levels gets wider, okay, because energy goes like L squared in this formula. And also the degeneracy of each value of energy increases. 1, 3, 5, 7, 9, and so on. Okay, so these 2 points are significant in the thermodynamic behavior of this system of rotators. Okay. Okay, so we're going to model a diatomic gas rotation part. So model the diatomic gas rotation part as a system of n rotators, and we assume that these are independent and distinguishable. So as a system of n independent distinguishable rotators. Okay. So each molecule is a rotator. We assume they're independent. That's a pretty good assumption. And we assume that they're distinguishable, which is okay because we've already taken account of the indistinguishability in the translational part of the wave function. So in other words, these rotators can actually be distinguished because they are all in different translational modes of energy. Okay. So that's our model, and we've seen that for independent distinguishable particles the partition function takes a simple form. So this is z, function of t, and it's defined as the sum over all single particle energy levels, so that's L goes from 0 to infinity, and the degeneracy is 2L plus 1, and then I have the Boltzmann factor, e to the minus epsilon L over kBt. Okay, and there are n of them, so this is to the power n. Okay, so this is the form we get for the partition function. So if we can calculate this, then we can find out all of the other thermodynamic properties. In particular, we're interested in the heat capacity, remember? However, you can't do this sum exactly. This sum epsilon L here is L times L plus 1, and you've got a factor of L down here. This sum cannot be done exactly, so we need to make some approximations. Okay, so I'll make a couple of approximations to see the kind of behavior of this function. So the first thing I'll do is a high temperature approximation, and in the high temperature approximation we can use a density of states approximation to replace the sum with an integral. I'll do that first, and then after that we'll look at the other limit, the low temperature limit, and see what the partition function looks like in that limit too. Okay, so this is our starting point, this equation here. Okay, so next then I'll consider this high temperature approximation. Okay, and here we're going to use the density of states. Okay, so what we're going to do then is say that z of t is approximately equal to, instead of summing over energy levels, you integrate over density of states. So integral from 0 to infinity, density of states times the Boltzmann factor to the power n. Okay. So to do that we need to find what is the density of states. Okay, so that's what we'll do now. So the easiest way to do that is to find, first of all, how many levels there are below a particular value of energy. So, how many levels with energy epsilon L less than some value epsilon? Okay, so this is the first question we'll answer. Okay, so the formula for epsilon L was h bar squared over 2I L plus 1, and this we need to be less than epsilon. Okay, so this means that L times L plus 1 is less than 2I epsilon over h bar squared, but this density of states approximation is valid when many levels are occupied. That means in practice L is going to be a large number, and if L is a large number then I can ignore the plus 1 in this term. So the high T approximation implies that the characteristic L is large, which means that L times L plus 1 is approximately equal to L squared, and then therefore I can rearrange this equation and get that L is approximately, at least, less than square root 2I epsilon over h bar. Okay, so this is the maximum value L can take, so I'll call this L max. So now our question, how many levels have energy epsilon L less than epsilon, is the same as how many levels have L less than L max. Okay. So therefore this is the number of levels, is the sum from L can go from anything from 0 up until L max, and we know the degeneracy is 2L plus 1. Okay, so if you use the following result, which hopefully you know, if I have the sum k goes from 0 to n of k, so this is 1 plus 2 plus all the way up to n, then this is equal to n times n minus 1 divided by 2. Okay. So here you see I've got a sum which looks like that, except it's 2L plus 1. So the 2L just multiplies by 2 here, so I'll get L max times L max, sorry, plus 1. That was a mistake. The formula here should be plus 1, right? Okay, L max times L max plus 1, and then this 1 here just gives me another L max plus 1. Okay. But again, if L is large, then we can ignore the terms of smaller value of L, so L max squared is here, we can ignore L max, and we can ignore 1. Okay? So the number of levels then is approximately just equal to L max squared, which from this formula here is 2I epsilon over h bar squared. Okay. So the number of levels with energy less than epsilon is approximately given by 2I epsilon divided by h bar squared. Okay. So therefore, the density of states, let's go up here, density of states is just given by the derivative of this function, right? So rho of epsilon is d by d epsilon of 2I epsilon over h bar squared. That's dead easy. This is 2I over h bar squared. Right. So now we can put this back into our approximation for z, and you get a straightforward integral. So z of t is approximately 2I over h bar squared, integral from 0 to infinity, e to the minus epsilon over kbt, integral d epsilon to the power n. Okay, and this is an integral you can easily do. This just gives me kb. So the final result is this is equal to 2I kbt over h bar squared, all to the power n. So this is our final form for approximate form for the partition function, which is valid for high temperatures. Okay, so now let's use this form to find what the heat capacity is going to be. Okay, so we want to find the heat capacity. So first we'll find the internal energy. Okay, so we have the equation for internal energy in terms of the partition function, this one. Sorry, kbt squared times the derivative of the log of the partition function. Okay, so the partition function, let me write it up here again. Z of t is 2I kbt over h bar squared power n. Right, so you see if I take log of z here, the n just comes down the front, and I've got log of some constants plus log of t. So this then is going to be equal to n kbt squared times d by dt of the log of t. That's easy, that's 1 over t. So this is n kbt, final result. And the heat capacity is per particle, let's say. So then we have to divide by the number of particles, so C is 1 over n times du by dt, and this is again a straightforward integral, this just gives me kb. So our final result is that in the high temperature approximation, the heat capacity of the rotational modes of the diatomic gas is just equal to the Boltzmann constant. Okay, now this may look familiar to you because this actually is just the result predicted by the equipartition theorem. So this result agrees with equipartition theorem. Which is to be expected because we said that the equipartition theorem is applicable in classical statistical mechanics, and the classical statistical mechanics is valid when your energy is large enough that you don't see the discreteness of the energy levels. Okay, and that's very similar to the high temperature approximation we've done here. So it's not surprising that we agree with the equipartition theorem result. However, the graph that I'd like to found is something like this. If you remember the graph we want for the heat capacity of the diatomic gas as a function of temperature, the translational part is 3/2 kb, but then we know it rises up to 5/2 kb, something like this, okay? And then at much higher temperatures it rises up again to 7/2 kb. So this part here, I claimed when I presented the lecture, this part of the heat capacity is given by the heat capacity of the rotational modes. So what I really like to be able to do is to predict a graph of heat capacity which looks like this. Okay. Goes from 0 up to kb. Okay. So our prediction here has given us the high temperature limit, which is just this line here, but we'd like to be able to study this part of the curve as well, and this is why we need a low temperature approximation. Okay. So next then we move on to the low temperature approximation. Okay, so again, if we write down the exact form we have for the partition function, see, this was the sum, L goes from 0 to infinity, 2L plus 1, e to the minus epsilon L. So explicitly this is e to the minus h bar squared over 2I kbt times L plus 1. All of that to the power n. Right. So in the low t approximation, t is a small number. So that means this prefactor here, h bar squared over 2I kbt, is going to be a large number. So for large values of L, this exponential function is going to get small very quickly. So if I draw what does this function look like in the low temperature limit as a function of L, then you get a graph something like this. So this is the function as a function of temperature T. It very rapidly decreases. Sorry, not as a function of T, as a function of L. It very rapidly decreases. So when L is 0, it's equal to 1, right? Because e to the power 0 is 1. But then it very rapidly decreases like this, exponentially quickly. And so if L0 is here, then maybe L equals 1 is over here, and L equals 2. By the time you get to L equals 2, the value of this function is basically 0. So that means in the low temperature limit, we can ignore values of L bigger than some number, because this function is going to be vanishingly small. Okay. So the simplest approximation we can make is only consider L equals 0 and L equals 1. Okay. So our approximation is going to be that only L equals 0, L equals 1 terms contribute significantly to the partition function z. Okay, so instead of doing the sum to infinity, which you can't do, I'll just do sum of 0 and 1, which is quite easy. Right, so we have then that z of t is approximately equal to sum L goes from 0 up to 1 only, 2L plus 1, e to all this funny stuff, all to the power n. Okay, now, which is equal to, if L equals 0, this just gives me 1, this gives me 1, so I get 1. If L is 1, this gives me a 2, this gives me a 3, so I get 1 plus 3 e to the minus h bar squared over I kb t, all to the power n. Okay? And if t is small, then as we said, this prefactor is going to be large, and therefore this exponential is also small. So what follows, we can treat this part, this term here, as a small parameter. Okay, so now just as in the high temperature case, we can calculate the internal energy and then calculate the heat capacity. So internal energy U is kb t squared d by dt of the log of z. Okay, so again the factor of n comes down, so this is n kb t squared d by dt of the log of 1 plus 3 e to the minus h bar squared over I kb t. But this exponential term is small, and we can therefore make the approximation log of 1 plus something small is approximately just equal to that small thing, right? That's the first order Taylor expansion. Okay. So therefore this is approximately equal to n kb t squared d by dt of just the small thing, which is this. So 3 can come out. I have d by dt of e to the minus h bar squared over I kb t. Okay, differentiate that gives me h bar squared over I kb t squared. Kb t squareds cancel, so this gives me 3n h bar squared over I times the exponential. So that's the internal energy, and now we can find the heat capacity by differentiating. Okay, so C per particle again, 1 over n du by dt. Okay, u is this, so if I differentiate again, I get another factor like this down the front. So I can write this as 3kb times n over I kb t all squared times, sorry, not n, h bar squared over I kb t all squared, yeah, that's right, times the exponential, e to the minus h bar squared over I kb t. Okay. So this is our formula for the heat capacity in the low temperature limit. So what does this look like? Okay, so for very small values of t, again this factor is large, so it's e to the minus a very large number, and therefore the heat capacity is exponentially suppressed. So at very low values of t, it's exponentially suppressed and it starts to rise up. Now if I go to high values of t, then this, for high values of t, eventually this becomes small, so this exponential is about 1. And you see that this is like 1 over t squared. So for high values of t, this function will actually curve back down again, like this. But for high values of t, our approximation anyway is not valid. Our approximation is only valid when this thing is a large number, and that means on this graph we're only interested in the bit of the function here, okay, the bit of the function where it rises up. So on this side, this is the low t part. So this is the part of the function which is valid. Okay. Now putting both of these results together, we can predict the final shape for the heat capacity. So putting both approximations together, we have the following graph. I know that for high temperatures the heat capacity is just equal to the Boltzmann constant. That was the result of the high temperature approximation. And we know that for low temperatures the function rises up, is exponentially suppressed, and then it rises up something like this. Okay, and so at low temperatures it looks like this, at high temperatures it looks like this, and if you join those two things together you will end up with a graph looking something like this. Okay. And that's good because this graph is exactly the right shape. So remember, what we were looking for is this part of the prediction of the heat capacity of the diatomic gas. We said that this part of the graph comes from the rotational heat capacity, and if you compare the shapes you see that this shape here is the same as this shape here. Okay, so that's very good. So our two approximations are good enough to show the kind of shape for the heat capacity graph that we expect. Right, so there's just a few points to make about this before we finish. So the first thing is, what is this scale of t here when the function starts to increase? Okay, so maybe I'll do this on a new slide. Okay, so we got a graph looks something like this. Okay, what is this critical value of t here when the function starts to increase from 0 up to something significant? Okay, well you can see from the formulas this starts to happen when t is about of a similar size to h bar squared over 2i. If t is much less than this, we're in the low temperature approximation. If t is much more than this, we're in the high temperature approximation. So this is the intermediate region. Now you can either calculate I from some quantum models of the atom, of the molecules, or you can measure it experimentally using spectroscopy. But typically, you find that this value, h bar squared over 2i, is somewhere between 10 Kelvin and 50 Kelvin. So that means somewhere between 10 and 50 Kelvin you'll start to see this contribution to heat capacity from the rotational modes. In other words, at temperatures much less than 10 Kelvin, the molecules are all in the rotational ground state, they're not rotating, but at temperatures much more than this you have a very large range of rotational kinetic energies. Okay, so that's the first point I wanted to make. The second point is we only did approximations, and our approximations are valid down here and up here. So we haven't proved that this shape is exactly like this. It could do something interesting in the middle. And in fact, if you get a computer to evaluate the sum up to the first, say, few hundred values of L, you find that there is something interesting in the middle here. The actual graph looks something more like this. So our low temperature approximation and high temperature approximations are right, but in between you actually get this bump, similar to the Schottky anomaly we saw for the paramagnet. So there is a bump in the heat capacity in the middle. This was not shown up in our approximations, and I don't know of an approximation scheme which will show this bump, but if you numerically evaluate the partition function to quite high values of L, then you get to see this hump here. Okay, so the final point I want to make, and this is the point which I got wrong in the original lecture, which is why I'm having to do all this again, is that the formula I use for the partition function is not always correct. Okay, so this formula, z of t, is not always correct. Okay, so the reason it's not always correct is to do with some subtleties of the quantum mechanics in the case where both atoms in the molecule are the same. So in particular, it is correct, it's exactly right, if the molecule is heterogeneous. That means if the two atoms that make up the molecule are different. Okay, so this is exact for heterogeneous molecules. Okay, so here heterogeneous means that they have different atoms. For example, something like nitrous oxide, carbon monoxide, hydrogen chloride. You will see that this sum is right, and you will see the heat capacity looking like this blue line here. Okay. But if the molecule is homogeneous, that means if the two kinds of atoms are the same, then some of the energy levels here are ruled out. That means the degeneracy 2L plus 1 is not exactly correct. Okay. So, but for homogeneous molecules, okay, so homogeneous means same atom, or at least the same kind of atom. So there are quite common ones: oxygen, hydrogen, nitrogen. Okay. For these molecules, some quantum, what can I say? Some quantum selection rules prevent some of the energy levels. Okay. So for these molecules, quantum selection rules okay, selection rules is probably not the right word. Let's just say quantum mechanics. And I'll explain more about this later on. So quantum mechanics rules out some of the energy levels. Okay. So what this means is that the 2L plus 1 degeneracy is changed. Okay, so in general for the homogeneous molecules, this sum is not quite right because we have to change the degeneracy factor here. Okay, so the simplest example, the one which is easiest to understand, is oxygen. Okay? And it turns out for oxygen, only even values of L are allowed. So even L can be 2, 4, 6, and so on are allowed. Okay, and you get different rules for hydrogen, different rules for nitrogen. Oxygen is the simplest, so I give this as an example. So why do homogeneous molecules have these properties? Now that I cannot explain without going into some quantum mechanical results, which I don't want to assume for this course. So to answer that question, why is this the case, I will do a kind of appendix lecture where I assume a bit more quantum mechanical knowledge, and you can watch if you're interested.